last stream with the checkers solver project, because I'm ready to shelve it. Main goal was achieved. We have a program that technically calculates valid moves, can progress through them, evaluate them, and in theory win the game. Although in the last stream we noticed that for one, it didn't make the best moves possible, or the moves didn't quite work out the way they should. So there was either very fundamental mistake in the map we generated, or it's just the comparison function. I'm just gonna simplify this now here. I'm gonna go with wins.compare to other.wins. We'll just go with whoever has more wins is the node we select. Let's see what that looks like. Just gonna ignore the draws and losses. So first move by blue. Right, promoted, looks good. Also promoted, not good. Defense, that's correct. That's not the best move that red could have made. Oh well. Yeah, this is just... They're not playing quite the way they are supposed to. But technically it's doing something, so I'm just gonna count that as a win. But the main goal for today is actually some optimization. Because I want to run a bigger board, and right now we're at the limit of what I can do without breaking something. One of the issues was the CalculateScore, where we had a stack overflow. So we have to take care of that. And I want to make the states smaller as well. Could we just take a quick look at the map once more? Just make a breakpoint here. So this thing has already 2,000 entries for that, well, relatively small board. And let's increase it to 5x5 with 4 tokens. Let's see if it can actually generate that. And we are going up. We're at 1 GB already. It's, again, you can't see it. I'm not sure why it's not recorded. Maybe because it's requiring special permission to the system. Maybe there's some elevated permissions that are granted for the view. Well, by 2 GB, I'm just gonna pause very quick. And return, we're in here, generate map. And I can't click anymore, which is fantastic. Hooray. Can I click here? Okay, that works. Let's see, and locals. The current map as it is. Notes. Oh boy, 4.4 million entries already. So there's a lot of stuff to store on here. So we definitely need to simplify what nodes and states require in terms of space. ChildNotes. Doesn't generate. right? That is add. I'm wondering if we should maybe sorry, I'm getting distracted. I'm thinking of a way to maybe just reduce it to a simple array, since the only time we actually add something is in here. But no, we're always adding something. It's just sometimes it's a node we already have, but it's always adding exactly as many moves as we have. So we store this ahead of time. So let's switch this out. That's a simple change. We can have crap. Get possible moves was an enumerable. But nothing too fancy. So let's store that as what? Wait, how many moves can we get? That's hard to say. I mean, we have upper bounds, which I don't actually want to use as a default. That's just, you know, whatever. I'm just gonna go with to list. Possible moves like that, and then node. Node child notes. Oh, let's switch that quickly to node array. Child nodes. Switch that to length. Length. What else do we have? That's that. Length. Okay. Child nodes equals new node possible moves dot count, and then we're gonna do index. Let's call it maybe child index to make that a bit more clearer. Child nodes, child index plus plus, next node. Like that. So child nodes itself doesn't change all the time, and it's only an array now, which should speed things up a bit, hopefully. How much do we actually just... we have the stage as a reference, we have a reference to the array, another reference to the scores. Yeah, it doesn't... I'm thinking of converting it into a struct to relieve pressure on the heap, but nah, not worth it. Especially since the nodes aren't actually gonna be deleted, so garbage collection won't have much of an issue here. Yeah, not worth it. Like, simplifying this, sure. But more than that, not necessary. CalculateScore. I need to switch that into a non-recursive method. It's all public, right? Yeah. You know, I'm gonna wait with that. I'm gonna do some fun stuff first. Like optimizing state. Let's see, what is left open for state? BitArray. That was something I wanted to change. I wanted to make a custom BitArray. What do we actually have here? 3 BitArrays. Which features do we use? Recursive new BitArrays, alright. Fixed size ahead of time. We access them individually with an indexer. To get booleans, sure. Anything else we do with that? Get the length, indexer again. Lots of indexers. Equals. We can simplify this, I guess. The equals comparing two bit arrays. Getting a hash code for the bit array should also be a bit easier with our own implementation. Alright, let's put down what we have. What's my cars? I just call it custom bit array. I don't feel very creative right now. And what do we need to do? We need public custom bit array, which will get the length. We have the constructor that does that, and we had the indexer, public bool this and index. What was it, like this? Get add something, and where to set. I still have to add the logic, but that's fine. Then we need the GetHashCode override. GetHashCode doesn't really feel all that correct. Let's not override the GetHashCode. That kind of implies a static reliable value, which we don't have, so I don't want to use it GetHashCode. It's not really a hashcode. When we do generate a hash code, it's not the same meaning as the method has. Public int. Just generate hash. Put that in. And public. Do we have a compare or just equal? We just needed the equals, right? Didn't, yeah. The comparison. Public bool equals custom bit array other. Yeah, I think that should be it in terms of interface. Maybe when we replace it, we'll see some alternatives we can use. Alright, first of all, custom bit array has a fixed length in terms of bits. And we're gonna store the data, of course, as a byte array. Read only byte array. Let's call it just bits. And this is gonna have length plus 7 divided by 8. New byte. And save this, and then. Alright. If you didn't know this, basically we want to take the length in bits, and we divide that by 8 to get the number of bytes. and the end result needs to be rounded up. So if we only require like 4 bits, we still need 1 full byte at least. So 4 divided by 8 would be 1/2, 0.5. We have to round that up to get the actual number of bytes as an integer. And to not have to work with floating points, this is something easy can do. You add 1 less than what you divide, and so from a length of 1 to 7, the division by 8 will always get, well, cut off, essentially rounded down towards 1. But as soon as we hit... Actually, does it? Did I make a mistake here? I think I made a mistake. Oh boy. It's always 1. I need 8. We get 15. That's still... No, this works out. So 1 through 8 bits would always go for 8 to 15 divided by 8. 1 in all cases. Once we hit 9 bits, we suddenly have 16 divided by 8, which would give us 2 bytes. So yeah, so it works. It's just a way to ensure that you round up when dividing integers. Alright, but it's one possible way to do that without any losses and without involving any floating point arithmetic. That's that. We should... How do I organize the bits? Do I go from least significant or most significant? Least to most. Makes most sense for me right now. So by default, everything is gonna be 0. So it's starting at just false. We could make quite easily now a method that quickly overrides the entire thing. Oh, and we can also make a quick way to copy this. Right, did I need to copy that at any point? I think I did, right? Let's move valid. Apply move. Yeah, it's copying all of the old data. Ah, okay, copy constructor. Forgot about that one. So we need that as well. Public, custom BitArray, copy. We'll have to do that as well, and well, that's gonna be easy. In that case, it's new byte array copy dot bits dot length, and then we're just gonna use array.copy. There was another, what was it? Buffer copy? No. Block. God, what was the other name? Copy. There was another predefined method for copy operations. Alternatively to just a simple array copy. But I think it had some specific uses where it would beat out array copy in terms of performance. But in general, array copy is pretty efficient, and when in doubt, always use that. Can't really make a mistake there. And the other is potentially dangerous, or potentially makes something wrong if you're not too careful. Can't remember which it was. Anyway, we're gonna copy copy.bits to bits for total length of copy bits.length. Right. Simple array copy done with special system calls in the background. It's not even copying by hand in a loop. I mean, it kind of... I think it's... Wait, there was some mem copy? Memory... never mind. But internally it would use some special calls in the assembly that use very efficient memory operations that just take an entire block of data and just have it moved around, which potentially is even then shifted off to just the memory controller. I'm not sure how deep the optimization goes in the standard libraries. I mean, even if that's possible, it's not going to do that on every machine, presumably. Anyway, the copy is there. Then let's take care of the complicated part. Getting very specific value for a specific bit. Okay, we have an index. And first we need to figure out which array index, where in the array we are, like which index in our bits array we need. And that's gonna be index divided by 8. So we don't need to round up. In this case, we need to round down. We're gonna stay at index 0 until we hit bit 8, at which point we go to the next index. So that's that. Array index, and we have a byte index. Maybe we can optimize things later. This is just gonna be modulo. Next, modulo 8. And actually we can make some optimization here. Divided by 8. Can just bit shift since we're working with 8. So the way I remember it, which doesn't always apply, again, it's optimization. The way I remember it, it was that typically division is slower than bit shifting, which makes sense. If you actually make a division, you have to either run some special code or trigger special hardware on your PC, which is probably going to be pretty fast, but involves still a lot of steps. Whereas bit shift is a very simple, straightforward ALU operation. So bit shifting is preferable to a division, but for some reason multiplication itself was faster than a bit shift as well, and I can't remember what the reason was. Like there was some optimization for which reason using a multiplication is actually ran faster than the bit shift. Like some weird voodoo happening in the background. At least that's the way I remember it. Whereas usually I would go bit shift is the fastest, because multiplication and division would require special hardware or something, but apparently that's not the case. And so that's what I always just do. At least if I'm somewhat conscious of performance. If it doesn't matter, then it doesn't matter, and well, if I'm wrong, it's not gonna change much. I just like the feeling of I'm doing something for performance. So division, slower than bit shift, slower than multiplication. That's the order in which I know things and gonna use it. And the modulo 8 can also be simplified by just using simple mask and actually just 7, right? We only want the first 3 bits. So for the array index, we take everything above the first 3 bits, and for the index inside the byte, we take only the first 3 bits. So this, which is just 7. Actually, it might make more sense to leave it at that, right? 3 digits here makes sense. Just to be clear that this is a mask, maybe write that as binary. Okay, and what we're gonna do is we're gonna go through bits, array index, and bits array index. We want to get a very specific bit. Yeah, we're gonna make an AND and build up another mask by going for byte index. And we use byte index, shift over a single bit by byte index. So if we target the very first bit inside the byte, that would be 0. Shift it over by 0 times, that's just a 1. Or shift it over by 1 if we want the second bit, index 1. We eventually end up with a 1, 0 or a 2. And that's how we get a mask with the bit set and exactly the position we care about. And if that end result is what's happening? What's happening? Like, keyboard, please do. Good. We'll go back to normal. That end result will be greater than 0 if the bit at the very specific position we care about is set. So is that greater than this 0? That's our boolean. Now I'm wondering if we just replace the variables with the calculations themselves. Can make it like this. You know what? Let's do it like before. It's not gonna really influence the performance. Pretty sure if this is gonna help, then the compilers will optimize it anyway. And this is way more readable. Right. Now the set is gonna be a bit more difficult. We still need the same indices for the array and inside the byte. But setting the value isn't as easy as before anymore. We need to either set that specific bit or we need to clear it. Alright, let's make an if statement, if value. So if we want to set it to true, if we want to set the bit, then we're gonna have to take the byte value we have in that array position and we have to set the specific bit. We can just take our mask, that's rather straightforward. And oh, right, all right. Convert bit to byte. So the bit shift is converting this whole thing into a byte, into an int. So we have to convert that back into a byte to make the binary OR or bitwise OR with the array we have in the, or with the byte we have in the array. Else we're gonna have to erase that, and to do that, we make a bitwise AND that has every bit set except for the one we care about. We can do that with the same mask, just inverted. And we have to do this once. Do we have to actually? No, okay. I wasn't sure about the precedence here, how that works out, but... So we still create the same mask and then invert it. So everything in that byte is 1 except for the 1 bit we care about, which is then gonna be 0. And that's combined with the bitwise AND, which will reset or clear that 1 bit. Actually, could we... Wait, I'm not sure if that works. Just curiosity. If I just take this byte mask like that. Can I invert mask directly and it's still staying a byte? Nope. Okay, can't. The inversion will not keep the type. Weird. Not too bad. I mean, I still could use the mask, but... Nah, this is good enough. Alright, so that is done. Let's take care of the hash. Does HashCode have something pre-built for... Okay, let's do new HashCode. No, I just have to... can only add values. Turn HashCode to HashCode. Ah, but HashCode... We have her at bytes. Which expects a span, which we can get by just feeding it in the array. And does it actually? Yeah. So this little symbol you see here, that's, I think that comes from ReSharper right now, from my add-on for Visual Studio. It's telling me that there's an implicit conversion happening. That's because byte arrays can be directly converted implicitly into a read-only span. Can they actually? No, not in... Actually, can they convert it in a span as well, implicitly? Let's quickly test that. Public, let's make a private void test. It's gonna require byte span. Can I test bits? Yep, okay, span works as well. So not only read-only span, you can also implicitly convert into span. Okay, nice. Span is, I'm tempted to say new, but it's actually not really new anymore. It has been new a few years ago. Type that it's like a wrapper around raw data. You can see, or not raw data necessarily, just it's a wrapper around another sequence of items. It's like it's a different term, a window. Like I can have an array and I can have a span the entirety of that array or just a specific part of it, and it's like having an IEnumerable, or do they count as... If I take a read-only span, Actually, let's make that not only bits, but a span. Span as a numerator. I also have an indexer, so that works. Do I have read-only? As read-only collection? No, that's not what I want. Read-only span byte. Does that work? Yeah, that works, and I can do something like this. This is specifically now a read-only span that targets specifically the bytes starting at index 10 and including index 10, 11, and that's it, because it only has 2 elements. And I can now read-only span 0, get the value at a specific index within the span on the original. So this index 0 in my span is actually index 10 in my array. And because it's read-only, I can now pass that on to someone else as a read-only span, and they can get access to exactly the specific piece of data they need, but can't change it. With a span, they could change it. And it's pretty nice, very convenient in a lot of cases. So implicit conversion, it's just basically wrapping my array into a span, read-only span in this case. And that's getting used by the hash code because it has an efficient way to use that, which nice. I have to look up what it's actually doing inside, because that's interesting. I'm gonna look that up now. No, resist the temptation. It's generating a hash code a bit more efficiently than what we did, spitting that out. And the equals, the efficient equals. Do we have an array.equals? Do we have an efficient way to compare? There was. Copy mem. I know there was some underlying method. Oh wait, that was. Now I remember, that was using some system calls. Some external calls that would do one-to-one comparison of the memory regions. Just compare the actual bytes in there, which is perfectly fine for us, technically. But of course, it's not quite the same as doing that all managed directly like this. Let's do it the classic way then. Still still more performant than what we had before. First, let's check if bits dot length not equal others dot length, others dot bits dot length, return false, because they need to have at least the same length, and if that all matches, then int I equals 0. Let's be fancy, let's do it in reverse. Because we're on the trip right now already. I greater equals 0. This one is 1. So the reason I do it in reverse, for one, actually that doesn't count anymore because I could fix that another way. I think the optimization here could help a bit. I think it's comparison to 0 is probably gonna have some more efficient method than, like, underlying systems will find out a more efficient way to compare a number to 0 than it will find to comparison with an arbitrary number. And I think I remember someone at some point mentioning that a for loop that iterates in reverse has another optimization that can be used in the background. But I cannot remember if that was actually talking about C# or a different language. Or what the supposed optimization was. I mean, they have their users, but it's not really doing a difference for us anyway. So in this case, I'm just gonna hope for the best and do it the way it's supposedly better, maybe. We're gonna compare the different positions. Can I do this? No, I can't. If it's not equal, other.bits I and false. I was wondering if I can do this branchless. But if I do that branchless, that means I don't have the option to get an early break out of this. And I have this branch, so to speak, anyway. For the loop. So no, wait, that's true then. Alright. Did I forget anything? We can create a fresh array. We can create a copy of another array, BitArray. We have an indexer that lets us get the status of a very specific bit. We cannot change those. We have a somewhat efficient way to generate a hash of the running total for that BitArray, and we can somewhat efficiently compare two BitArrays. Maybe let's make another single change in here. If length is less than 1, oh yeah. Kind of name exception, actual value length must be at least 1. Yeah, so we avoid problems with zero length. Alright, then let's change BitArray. Let's make it like that, and like this, match whole word. Some bit array. Let's see if that breaks anything. Did break a lot. Okay, so forgot the length. Public and length. Bits.length. That's better? Yeah, but another issue is here. That's the hash code at... I'm wondering... Generate hash. Add as hash. Hash code. Hash code. Can leave the hash code in there, but then we can just go for occupy.add as hash. Hash code. The same for color. And promote it. Otherwise, we'd have to call the hash method that calls just add bytes on a new hash code, which is fine, but instead we're just adding to the existing hash code, which is presumably much more efficient. Or maybe not much, but maybe. This should work. And equals, yeah, equals count? Wait. Wait, did BitArray have two versions? BitArray.length? Okay, so it does have both with different meanings. We're just gonna use length, and we're just gonna use it as a read-only. We're not gonna change that. Alright, but with that, our custom bit array is done. And we have some more, hopefully some more efficiency in that. So it's not gonna really save us any space, I presume. It's just gonna add some more efficiency and operation. Oh, the equals, forgot the equals, sorry. And we compare those, and all right, let's push this up. If those don't match, we return false. Equals other dot occupied not. Okay, next is color, and finally promoted. Like that. All right. Can actually drop this. Let's clean this up. Okay. Doesn't look bad. We're gonna leave that as is. I'm not gonna touch that for now. Let's quickly check if it's still working, at least the way it should. Let's reduce the numbers. Well, I take that as it doesn't work the way it should. Great. Alright, let's quickly look over the methods. Was there anything obvious? Okay, it could be that these methods are broken. I'm gonna have to check that later. Anything else? That should be fine. This is comparing the bytes. No, that should be correct. So, if anything, it must be in here. Guess we're gonna quickly check that. Okay, we're setting a value. Let's see, what is bits currently? Yep. We have only one single byte, which is currently 0. Alright. Array index, byte index, 0 and 0, which matches. Index was 0, so everything looks good. And we want to set the value. And outcome is 1, which is correct. So that is correct. And this time we want to make sure the value is 0. We want to unset the bit. Which, yeah, it's doing okay. That wasn't that hard. And let's try once more in this case. Still 0, still unsetting, not much happening here. Oh, this is new. Index 6. And it's setting the bit. Alright, this is something new. Array index is 0, which is correct. Byte index is 6, which is correct. I mean, we're only working on one single byte right now, so of course it's the same index. And we're setting the value. So what bit do we expect if we set bit 6? That's... $28, 64, 65 should be the end result. That's correct. Sorry, I had to make sure that I got my powers up to correct. Alright, so in this case we're still setting index 6, but this time on a value of 0. So just 64. Correct. What else do we have? Index 6. This time unsetting. Well, it should be just 0. Correct. Now we're gonna set index 1. Yeah, byte array, array index and byte index correct. We're setting the value. I'm setting index 1, so we should be 67 now. Well, that looks all pretty much correct. Let's jump forward a bit. Oh, we're getting a value? Okay, let's see if that works. Array index, byte index, yeah. Value is 99. We're checking the value at index 2. Indices down here are correct. Ooh boy, what is 99? Which bits are set to 99? Let's see, 64 must be set. 32 must be set, so 6, index 6 and 5 are set with 96, then 3 missing, so bit 0 and 1 are also set. Index 2 should be 0. Which is correct. We'll return false. First line here. So that is correct. I'm wondering what's going on here. Okay, let's just quickly... I'm lazy, so we're gonna... copy that stuff out. This was the new code. This is the old one. Which still valid, and the hash code generation. This is the new stuff. Okay, that's an enumerable for the different bits. Is there an easy way to do this? I don't want to create an entire numerator for this, I'm too lazy. I could make an iNumeral method. Just call that instead, so let's do that. Public enumerable bool. Alright, bits. Let's call it like that. And what we're gonna do is, well, we have to go through each byte of the array, so we'll just iterate through that. Let's just call it B, and in there we're gonna, actually let's make it easy. Yield return. Actually, doesn't that... wait. No, that's the end result. We can't use that. Yeah, let's just... B and... there will be 0, 0, 0, 0, 0, 0, 0, 1, 0, like that. And put that up with 3. 2. We could make a loop for this, but I feel like this is, in case of just 8 statements, this is gonna be fast. I mean, we're generating a full state machine anyway, so I guess it doesn't matter anymore, but actually gonna just clone this, do that, then we're gonna do this. Okay. Yeah. Gonna do it like that. Occupied.enumerate bits. Okay, this is pretty much the old code. Still has that weird behavior. All right. Then let's switch that with the oh wait. Current selection. There. Was too lazy to do that by hand. Would have probably been a bit faster. Oh, well. So now we use just the BitArray again, and it's generic. So back to BitArray, and this one works. Okay, we definitely have a mistake in our custom BitArray. Just the question is, where? What is it that we are doing in our custom BitArray that's breaking the whole thing? Actually, let's use the new code as well, since we're... Leave the old one in this time. Just as a reference, maybe we're gonna use it later. But this should not... This shouldn't have this different behavior. Player 2 wins. Why is it deciding that player 2 wins? Well, you should start there. Try to go backwards. So when we hit the breakpoint here, we're gonna be in the very first starting state, and this should essentially tell us that there is no possible move left. We need no more children to add and anything. Is index wrong? Nah, that can't... Not. Nope, no. Index 0 is possible. Okay, decides that move isn't valid. What are we technically... What are we actually talking about? X1, Y... X1, Y0. Oh, we don't have it highlighted right now. We are... talking about the entire board. So it is, yeah, it is the first blue piece, top left. And the offset we're looking at is -1, 1. Okay, that's fair, that's invalid. Yeah, that makes sense. Target X to target Y, okay, that's invalid as well. Just positioning is invalid. Okay, let's see. Target X is 2, target Y is 1. That should be a valid move. It's not considered a valid move. From 0 to 3. That is the correct move. Why is it not valid? Service capture is false. Move the token. Ah, doesn't matter anyway. Wait, why is length 1 here? Ah, okay, it was an obvious one. Yeah, yeah. Let's just see what it's doing now. Yeah, now it's working correctly. Okay, that was a very, very dumb mistake. I was returning the length of our byte array, but what I'm interested in is the length of our bit array, which is, of course, 8 times that of the byte array. Wait, Wait, it isn't. It isn't. Oh, still have a mistake in here. Because the last byte is most likely not fully used. So we'll have to actually keep track of. Okay, that makes this means this is also kind of nonsense anyway. Let's drop that. Never made any sense. And that also doesn't make sense. We have to actually. Oh boy. Okay. I have to actually store the length of the whole thing. Private. Actually, why not make that public then? Public int length. Not calculate that and instead just store it in here. Length equals length. And here as well, length copied on length. Yep, that's correct. And we compare the, not the bits length, we compare the actual length, which can be different even though the byte arrays are the same length. And if they are the same length, since we don't allow any changes, we know that the furthermost bits, the unused bits in the last byte are gonna still be 0. We also need to make a quick check in here. If index less than 0, branch exception, index at least 0, and if index greater or equal to length, must be less than length. Same here for setting. So we definitely know the unused bits in the last byte are going to be 0, so we can compare the entire byte without worrying about cutting off the unused parts. All right. Yeah, that was obviously wrong. Let's try again. Yeah, much better. And let's drop the old code. Don't need it anymore. Get out of here. Oh man, that was a really obvious mistake. Right, got that now. And that is all correct now and optimized. That means now comes the hard part. Ooh, don't like that. Okay, first of all, notes. Do we need to change notes in any way? I don't think there's much we can optimize here. Without understanding how big the whole thing grows, we can't really make any good predictions about how much memory to reserve, so let's just keep the default dictionary logic. That can all stay. Let's quickly check, if I do that and that, it used quite a lot, but did that happen in the calculation or the Yeah, that's using a lot of memory already. He says while looking at not even 50 megabyte. Okay, I'm gonna say that's a good sign compared to the BitArray. Okay, you know what? Let's go back to this state. Let's that's the old code. That's the new code. Let's put on the old code again. I want to test something. I want to have the direct comparison. Means we have to actually do the enumerate bits part. No, we don't have to. Okay, that's the code, and then we're gonna use custom bit array, replace that with BitArray, and we're gonna replace that in our selection. Yeah. All right, so our BitArray is back in. It's using the old code basically. I'm creating a board 5x5 with 4 tokens, and we have a breakpoint for CalculateScore. So all we're doing right now is just setting up the tree. We're not evaluating the tree yet. We're just gonna check how big the memory. Okay, we had 200 megabytes, 300 megabytes, 500 megabytes. Okay, I'm just gonna let it run. I'm curious how far it can grow. But I'm gonna make a cut at, let's say 5. No, let's go for 7 gigabyte. If it hits 7 gigabyte, I'm just gonna board. It's at 2 gigabyte now. To 3, to 4. It's at 3 gigabyte now. I'm just giving you the numbers I can see. 3.5. 4. Get 4 gigabytes. GB. 4.5. Garbage collection is not happy. We're at 5.567. We're at 6 gigabyte now. 6.5. I'm hovering over the pause. Oh, we reached the end. We're at 6.6 gigabyte on reserved memory. And let's look, we have nodes. 29, that's 15 million? 941, 265. Yeah, 15.5 million nodes. 6.6. See, that's 15562 941 and 6 gigabytes. Okay, let's stop here and now go back to let's drop that, bring that back in, drop that. So go back to the new code. Everything is using custom bit array. Alright, let's repeat the whole thing. We should get the same result in terms of nodes. Now it could be that the memory doesn't grow as fast because the process is slower because I messed up somewhere. That is entirely possible. We'll only know once it's done, but we are at 40 megabyte now. Also interesting, the diagnostic tools, they have this little indicator for activity in the garbage collection. Little yellow check marks. Previously it was completely full of that stuff, and right now it's not. And we are at 50 megabyte now. And it's slowly rising. We're at 52. There are little steps in between. Oh, that was a big step. We're at 57 now. From 52 to 57 megabyte. Still only at megabyte. I didn't record how fast everything worked. Should have done that as well. I mean, it's in the recording, I can check that later. Should have kept track. Oh, there was a little drop in memory actually this time. We're at 61 now. I dropped from 62 to 61 after a little activity of the garbage collection. It seems like the garbage collection isn't under any pressure since there isn't really much memory in use. So I guess that's the reason. Before, when we had the many gigabytes, there was a lot of pressure to keep the memory clean. And right now we only had 63 megabytes, so the GC doesn't care. GC doesn't give a fuck. So that's 64 megabyte. We've reached 65 megabyte. 66, 67, 71. Oh. Seems we've hit some kind of growth. We probably have some new nodes. The tree is spreading out. 71 megabyte. Still pretty slow. I'm wondering if I just have a mistake in my code, but it did work earlier in the simple test. Okay, I'm pretty sure it is slower than the old code. Though I'm not sure why. I'm not sure what's so much fast about the bit array. But honestly, it seems like it's worth it. Like right now I'm 73 megabyte. Like that's 0.1% of the memory we used before. That's massive improvement in terms of memory. Totally worth the extra waiting time. I'm just gonna claim it is. I don't actually know if it is. But yeah, it's 75 megabyte. It's still not progressing. Let's make a quick pause, see where it is. Crap. It didn't like me switching up the... Ooh. It crashed the entire process. It didn't like the debugger interfering. I don't want to redo it. I don't want to redo it. Let's try the old code again anyway. Wait, only change this, right? BitArray, custom BitArray. Right. Should my life... Yeah, I could make my life easier with pre-compiler directions, but... Okay, that's that. That's the new stuff and the old stuff. That works. And... Custom BitArray replace with BitArray. In selection, replace all. Yeah, and include that. So they're using now. Alright, and let's make another test, but smaller scale. Hopefully this is a bit faster. And... Okay, let's leave that in. That was an interesting stat, but let's make a new one. So, old code. And we're done already. Okay, that was fast. We're using right now 121 megabyte. Let's make a bigger number. Let's use a bigger number. This is a bit... Let's use 4 tokens. Yeah, more moves significantly increased the amount of stuff we can do. Alright, that's still a bit... We can do more. We can do more. Let's go to 5. Let's see what we can do with this. Okay, that was even faster. Let's go for 4 again. Now let's go for 5 and height and 3 tokens. I'm looking for a sweet spot where the test is relatively fast, but has big numbers. Okay, so roughly 10 seconds for calculation, and we're at 633. 10s. 3 megabyte, and Notes has 1482341. 143. Wait. Yeah. Okay, so that's the result with the old system. BitArray, custom, custom BitArray. That, and we're gonna cut out the old stuff, bring in the new stuff, cut out the old stuff, bring in the new stuff, and run the program again. It's definitely taking longer. Why is it taking so much longer? At this point I have to assume that I made another mistake somewhere. That it's not doing the same program. Because this doesn't make any sense. This is... With 50 megabyte? We've definitely lost speed, but where? What is BitArray doing so much faster? I mean, it has to be BitArray. That's the only explanation. Right? We're at 2 minutes, 60 megabyte. Okay, let's make a little pause in here. Hopefully it doesn't break this time. It broke again. And we're still stuck at the equals. I have to assume that the equals method is the big issue then. Alright, that's now. Okay, I clicked the wrong button. Just give me a second. Yeah, now it works. We're back. Currently in the process of restarting Visual Studio. Right, so old code, new code, and actually, why don't I just rename this to BitArray like that? Still using BitArray everywhere, so that's easy enough. Just using our own BitArray, and then define old. Oh, okay, sorry. Yeah, define there, to use there, define old. And then let's switch the code up here. If not old, that, else. Gonna put in that. If alt else that. Right. So now we have a simple switch, sort of, to run through that. And all right, let's do it. At this point, numerable byte. Actually, can we? Oh, doesn't matter. Enumerator. Private enumerator. Let's get some practice in, I guess. Class. Nope, not like that. Class. There. And it's gonna be an enumerator or byte. Wait. That's not what I wanted. But we can start with public enumerator BitArray source. Let's call it that. Reference to where we are, and private int array index, private int wait, no, it's not doing that. Meta. Whoa. Actually, do we need that? I think the for each can do without, right? As long as I have a get enumerator, that's fine. Yeah, it doesn't need all the fancy stuff. And if that's the case, I can simplify this to just index like that. 0 bool turn new enumerator of this, and then implement the missing members. Next, actually, right. We don't need those. We should start with -1, move next. F plus index less than source dot length. Not if, just, yeah, that's good enough. Reset index equals 0. Current source index source index dispose doesn't need to do anything. All right, so simple enumerator, so we can use one-to-one the same code. Old. Okay, so right now we're using the old code. And fine custom array. Gonna make it like this. Custom BitArray. Right, so now I can just change things like this. If I do this, then everything's going to use the system collections BitArray, and do that, and just as a precaution, if not CA define mode. Right, so if I don't have the custom EA, I have to use the old code because the standard BitArray doesn't work with the new code. But if I have the custom BitArray, I can actually use old or new code. Okay, right now we have the old code. Just try that once more. Old code with the standard BitArray from the system library. And we're getting 7, 8, 9, 10. Yep. Okay, this time it was a bit more memory. We're at... No, actually, no. 631 megabytes. So it's roughly the same. Same amount of nodes. That shouldn't change at all. Still 10 seconds, more or less. So that worked. Then we're gonna use the custom BitArray, but with the old code. 4, 5, 6, 7. 8. Gouge collection is definitely more busy right now. Interesting. So it took 12 seconds, more or less, and we're at, yeah, 630. It's about the same. It's just taking a bit longer, and the end result 1482341 looks the same, so that's correct. We're using the custom BitArray. I think it's referencing the custom BitArray, right? Yep, it's our own BitArray, but it's using the old code. So the issue is the code. Okay, let's switch this around. If I try this again, but with the new hash code, does that change the outcome? It's taking longer. We're only at 30 megabytes. What is going on? Let's get in here. Let's maybe make a breakpoint. Yeah, we're only at 40,000. This is... Alright, this is interesting. So... the presumably faster hashing system is significantly slower. How? What about the comparison? We changed the comparison out. What's happening? Oh, right. Restart. Okay, memory is growing a lot faster. Yeah, that's 10 seconds. Right about 600. Yeah, we're at the same state. Everything is right. So the equals method can use linear code, that's fine. And it does actually gain some speed again. Though we're talking about only a few seconds. This is not proper profiling. So that works. Why is the new hashing slower? Okay, what happens when we... Alright, hash. What if we do this? It's new hash code and return to hash code. We use generate hash code in here and gonna use hash code at generate hash. We're gonna do that for color as well and for promoted. Let's see how this fares. Memory is growing fast. Wait 6 seconds. About 6 seconds. Memory consumption is pretty much the same, but it did speed things up. So this is significantly faster than this, which makes sense. But why is this so much slower? Generating the hashcode in chunks and then adding the end result, or combining the end result into one large hash, is faster than generating everything in one go. Alright, let's look up how the hashcode actually is doing it. That's the wrong window. Let's go over here. Let's see. Good old source.net. And you can see what I'm doing, can you? Can I just quickly add a browser window? Let's see, plus. Not browser, window capture maybe? Window capture, there we go. That. Fine. Okay, so this is where we are, hash code. So this is what I do when I don't know what's going on. Looking up source.net, let hashcode, and let's quickly check on what the add bytes is actually doing here. Okay. If we have at least 16 bytes to hash. I'm just adding something that, okay. So let's see if we can figure out what's going on here. Or if I can figure it out. Maybe you have a good idea. So, position ref, get reference value. Get reference. Okay, so we're literally generating a ref that targets the specific memory addresses. If I get that right? So position and end are basically like variables that target the exact same part of memory that our original array would be at, with the first and last byte respectively in the array, since we pass on the entire array for value. I have actually a go-to here. Oh god. Size of int. It's gonna be 4. Yeah, that's the 16 we have mentioned here. So if the... No, that's not what I wanted. Let's go back. If the total length of the array is less than 16, we go to small. Down here. In our case, that is the default. That's actually what's going to happen for us most of the time. At least with the 5x5. Yeah, that's 16. our BitArray store the black squares on the board. So yeah, we're definitely below 16 so far, at least for our current board states. And small is just byte offset. Ref position, ref end. Alright, we're just reading, underlined, ref position. Okay, we are just literally iterating through the byte array, taking 4 bytes each. Like this whole thing is just to iterate through the byte array without knowing that there's a byte array, because we're technically working with the span. It's doing some unsafe wizardry, but that's still understandable. It's as long as there are at least as long as there are at least 4 bytes left, call the add method with an integer that is just generated from the 4 bytes. Doesn't mean that it actually represents an integer or is intended to represent an integer. We're just gonna take the data as an integer, as a collection of 4 bytes. And then we're gonna move the current position forward by 4. And then once we hit a point where there are less than 4 bytes left, we're just gonna add the individual bytes, but still treat it as an integer, where just the upper bytes are filled with zeros. Ref unsafe add. Yeah, moving forward. So it's just going through the entire array and calling add all the time. Why is that so slow? I don't get it. Since we're calling the exact same code anyway. Okay, so that code is the same, so it's not that. It should be with the add. The difference would be that in one case we're calling add on the same object constantly, and in the other case we have individual iterations of the hash code where we call add. Is there something that's... Just reading the text right now, trying to see if there's anything useful in here. Oh, lovely. Thank you for the tip. Okay. What's it doing? It's taking some values. Okay, length is... Okay, we have the... const params, that doesn't matter. V1 through V4. Q1 through 3 and length are all internal values that change over time. So they have an influence. Length increases. Switch can't be inlined. Oh, that's interesting. I always go for switch because it's being broken down to if-else if necessary, but switch can't be inlined. So there's an optimization for... That's good to know. All right. Length. Position. Okay, position is constantly iterate. That's correct. Just taking the value, converting it to U, and okay, that's fine. Q2, Q3, else. Initialize. Wait, how many? Could that be it? Right now our BitArray is pretty small. Like 1 byte large, right? With the 5x5 board, right? What do I have? 5x5 board. These are with, let's see, 2, 3, 5, 7, 10, 12. That's 12-bit. So 2 bytes per byte array. And we go through those with the small method of small part, which is going through in steps of 4, which means we're just adding integers twice. Actually, no, not even twice, just once. One call to add with a single integer. So for the method where I'm calling a new hash code every single time, I'll just combine those in the end. Those byte arrays would only ever get position 0. Fill Q with a value, Q1, and that's it. We never hit the initialize or the rounds. What are they doing? Those are constants, right? Generate static read only. Okay, yeah, it's wait, how is it? Oh, okay. I didn't know interpreted random bytes. That's good to know. You learn something new every time you read the source code. That's quite nice. But seed is staying the same. Primes, we had those. So initialize is pretty harmless. What about round? Bit operations, rotate left. 13 prime. Seems harmless. Yeah, it's pretty harmless. It's just shifting around the bits a bit, but nothing heavy. Just some arithmetic operations in here 4 times. So that's not really doing much. Is the hash code doing anything differently? Those are not doing anything. Those are also pretty... I don't get it. I don't get it. Yeah, no, 6 seconds. That's pretty nice, pretty fast. But if I go for adding them all to the same. It's suddenly extremely small. Yeah, it's very, very slow. Why is it taking so much time? Okay, let's have a quicker look at this. Let's quickly see. Let's see how fast this is. Something that should not matter that much. No. Okay, let's use stopwatch. Not the best for profiling, because there's a lot more to it, but in this case it's very extreme, so we should be able to... Wait, I just noticed you can't see it. There we go. I'm back in the code. Stopwatch, start new. I just keep that stopwatch and split this up. And start new dot elapsed ticks. If start new elapsed ticks. Actually, let's just see what we get. 45, 1945. Seven. Okay, let's maybe make if elliptic greater than 100. Take more than 100 ticks. Let's maybe figure out what's going on. Oh yeah, 1000. There we go. Something big happened. 16. Another 130. What is happening here? We're in a state which has 2 bytes. 2 bytes, yeah. Why is it taking so much time? Let's try the other code, switching this out. So with individual pieces, do we ever get to the point where, yep, we also had big points, but that's not... Okay, how do we actually profile this now? I know the hash method has an issue, but I don't know under which circumstances. And I could start just logging that stuff. Could start just printing it to the console, but that's gonna take time as well, and I'm afraid that's gonna mess with the measurements. I don't really have experience in profiling, so I don't know how to handle this now. Why would one be faster than the other? I didn't see anything in HashCode that really tells me what's going on. At the same time, I love this and hate this. I love it because it's interesting conundrum. It's a puzzle. Figuring out what's going on is kind of cool, but it's also, I have no idea where to start looking. See, at work, I would just accept this as, okay, one is better than the other. Let's go for it. And I mean, this is, with that code here, it's faster than the previous version for BitArray, which is good. We improved the performance quite a bit. We didn't save on memory, so that didn't change anything. That wasn't expected anyway, so that's fine. It's just performance improvements in terms of time, which is huge already. But I'm still bothered by this performance improvement through the different hash. Why would that make a difference? Okay, let's maybe make a little example here. Let's see what happens if we do this. You go for add as hash, but what we do in here is we generate hash, and then hashcode.add. So that's the same code as we have. That's the faster version. We generate individually and then just add it. And with this, I want to just check if using the reference, making all those method calls and giving the hashcode reference around somehow affects it. Oh boy. It does. What? Like I'm doing this. Calling hashcode.add with whatever generate hash. Add as hash. Calling generate hash, add that. Yeah, it's slower. That's the issue. But how? Like, why is that? How is this one method call so much slower? Return notes. Let's just do this. Let's remove the breakpoint. Turn. So if I do this. Oh wait, should stop. I want to see if the debugger has any effect on that. So I'm just starting the program without attached debugger. Letting that run for a bit. It's not so... No, it's still slow. Let's try the release version. Three, 4, 5, 6, 7. Doesn't seem to be a lot of improvement there. So it's not because of that. I was thinking maybe some optimization getting in the way. That is so weird. Okay, what if we change this to a ref? Maybe an in. That make a difference? Yeah, let's just keep it at ref. Let's see if that's affecting this. This is so strange. Yeah, and suddenly it's way quicker. What is... How? What? Was something special about hashcode? Oh, wait. Yes. I'm an idiot. So here, hashcode. Was just checking, is there something interesting about it, and just... I forgot, it's a struct. It's a struct. So, of course, what was actually going on here is when I called ls-hash and passed on hashcode, I would create a full copy of hashcode of that struct, pass that on. Which also means that the end result was wrong. So first I had the copy, passed that onto this method. This copy was changed, but then the copy was never returned. So it had to make the copy once and completely disregarded all the results, which of course then messed up the entire algorithm, because suddenly the hash code was only determined by these three, which barely change. That means the dictionary had suddenly tons and tons of conflicts because all the different states suddenly had the same hash code. So just to confirm that that's the correct assumption, we're just gonna do this and then return hash code. And we're gonna... Now this is still slightly slower because we are still making copies of the... What's going on here? Of the struct, but it's actually doing the right thing now. Oh yeah, memory is growing fast. Yeah, now it works. That was the issue. This was just a genuine bug that created the wrong hash, which basically meant that it's always generating basically the same 5 hashes. If anything, actually the same 2 hashes, which means tons and tons of conflicts, which meant that the equals method had to be called constantly. It was basically, we didn't have anything gained from the dictionary. It was treating this thing more like a list, where it had to compare every single item every single time. So, of course, things got a bit slower. Wait, that's the wrong one. I didn't want that one, I wanted this one, the new system. All right. Yeah, we definitely want the custom. So put that back in. Hashcode dot hashcode. So our little trip, to the hashcode struct was interesting, but the problem was somewhere else. And we're gonna revert this to a ref once more. And that is hash, that's fine. Can be void ref, node add. That also means we can do hashcode dot add bytes bits. Can drop that. Which in fact should speed up the whole thing in theory. Yep, we're at 6 seconds and about 3. So we're at the new system with about 6 seconds now, with a new bit array. So definitely improvement in terms of speed. Didn't save on memory, but did save on speed. Cool. Ooh. It only took us 2 hours to save 4 seconds. Well, at least in this example. Let's see what happens if we increase it a bit. And let's make a breakpoint back in here. So memory is growing. We are at 900, 1 gigabyte. I'm wondering if the upgraded speed gets us to the result also quicker. I think the 554 is what we did in the beginning runs, right? Which had the 6 gigabyte. We're at 3.5 gigabyte now. I feel like it's faster. Forgot to take the measurement with the old one. But I don't want to redo that. 5.5 gigabyte. That means we should be close to the end, right? Since it's using basically the same amount of space. 6.3, 6.4, 0.5, 0.6. In 1 minute and 8 seconds. I think that's pretty nice. Let's see, notes. Oh god, I don't want to do that. I want to have some specific information about nodes, but I can't get that information without... Okay, let's just do it a different way. I'm curious about nodes.count and nodes capacity. What's going on here? Okay, this is gonna take another 1 minute 8 seconds, presumably. Just gotta wait for it. I just want to know how much of the space reserved in the dictionary is unused right now. How efficient are we using, or how efficiently are we using the dictionary right now? It's not gonna help us much. I mean, the dictionary is not gonna take a lot of space because it's just storing the references. Both state and node are classes, it's just references. But there might be some potential. Maybe we can compare the capacity to the count sometimes in between generations and then make a trim if we think that it's not going to grow. Oh no, actually that's wrong. Let's wait for it. 5, 6 should be 2, 1. There we go. All right, so capacity is quite a bit extra. So let's just make a quick notes dot. Was there trim access? Yeah. That's the one. Let's see what that's doing. Okay, and one last attempt. Let it run again. 1 minute 8 seconds seems to be pretty stable. God, I'm so thankful for the new upgraded RAM. A while back I bought myself a new PC. The old one has served me for... God, when did I get the old one? 8 years, I think. It's still pretty good. I splodged a bit back then. It's still pretty good PC. I just passed it on to someone else. It stayed within the family, you could say. Not just you could say, it did stay in the family. My parents now have a fully equipped gaming PC to surf the web. Very useful. I'm joking, but not really. And with the new one, I also upgraded my RAM a bit, because I noticed for development I was hitting the limits quite often. And we are there. Alright. I'm at 6.6 gigabyte used memory right now. And now I'm at 7, so that was a good decision. Let's use... Okay, I'm creating a snapshot right now. Taking a while. Actually, you can see that one at least. And no snapshots available. What happened to my snapshot? Did it abort? I'm confused. Let's try once more. Did I accidentally click cancel snapshot before? Nope. Probably doesn't like that. I do have a tool technically that lets me look into the heap. But I don't have experience with that, and I haven't set up anything for testing that on live on stream, so let's do that. I have to assume that the memory is mostly going to state, which is split into various references within Node. Well, let's see. CalculateScore should then now reach an Stack Overflow. Yeah. Technically still need to change CalculateScore. Let's see, CalculateScore is that method. Okay, why do we have a recursion? Whenever we call CalculateScore on another node, okay, we start calculating on a node, and alongside that node we have to store the number of visits. Visit is public, just a field. Make all the references based on that node. I'm currently thinking about the best way to turn this into just a stack and a loop. way this operates is basically depth first. We always go to the first child. Okay, so that state is simple. That's also simple. Make a resize here. It's a done deal. The only part where we actually do have to take care of recursion is that. For that we can store an index that lets us know how far we are. Alright. Let's try something. Actually, let's copy the entire method. We'll make it that as a separate method for now, because I don't want to mess up the code in here and maybe simplify things a bit. So we have initial node, yeah, just node initial node, right? Add everything in here refers to a node. Let's see, we're gonna have a stack, and the stack is gonna contain the node we're talking about. Let's make that a tuple. We have the node of interest and the version of previous visits. So when we add a node, I'm gonna add it with the number of previous visits. Let's call a stack. Stack dot push initial node. Well, it's gonna be 0. Node dot visits. Actually, no, wait. No, that's correct. Plus visits. So that's just predetermined stuff. This is what happens on site. So I'm wondering if it's better to have 2 stacks. Let's do it in 2 stacks. So we have 1 stack for the nodes. Stack. I have no idea how deep this can go. It would be great if we had an idea of the deepest depth we have. Wait. Can we generate that? Generate map? Not really. I mean, I'm sure we can figure it out somewhere here, but okay, let's not get into that. Let's just accept the stack as it is. Node stacks, and we have the other stack for previous visits. Visits. And we're gonna nodes.push initial nodes. Okay, and then while nodes.push length count greater 0. Gonna take. Okay, first make previous visits dot push nodes dot peak dot visits. So we're recreating this part. We're storing that in a stack. So first we're gonna store the previous visits inside a node, and then actually let's not do it that way. Wait, do we? Can't I just pop the node? Do I need it again? Need to reset it later when I actually drop it. No, I can't do that. Can't pop it yet. I have to wait. And current node, peak. It's that, and then previous visits, push current node dot visits, and current node dot visits plus plus. Oop. And right, the index is something I also need. That means we have a third stack. Wait, maybe I can use it after all. No, I can't. That thing is constantly reducing. Never mind. Essentially, I have to kind of have a state machine now, which tells me how far I've progressed in this method when I visit a node again. Thing is, I know these will happen in one go. The only way I actually have a state left for a node is when I'm in the children. Otherwise, I would have everything finished already. And that means I can use the index as an indicator for which child I am. So how far I've progressed in here. This is the breakpoint or the interruption where I actually do have to switch, which basically goes to a new state. And I have to keep track of that state as well. So I have the variable, like the local variable I have to store within the method, which would be part of the stack, and I have the node itself. Maybe I should make it one stack after all. Makes things a bit easier, I guess. But that makes it harder to change. If I'm just an integer and a value tuple, I can't change it. Okay, let's make it slightly different. What if I have a... Okay, just an idea. Just call it frame, because I'm original like that. And we have a public node, public int previous visits. This is a visits, and the public int child. That should be fine for a struct. And what we're gonna do now, we have frames. We're creating a stack with a frame being an actual representation of the node itself that we are interested in and the values we are interested in. Push a new frame. Node equals initial node, like that. All right, so let's change this up again. Frame.peak. So that's our method basically, and then still gonna do the same stuff. Frame.visits equals frame.node.visits. Frame.node.visits. Just plus plus. Let's simplify things. So that's taken care of. Then we have to do all of that. And if frame.node, yeah, that's the one we need. Frame.node length, node. Everything with frame.node. Wait, that was not, that was just node.maximum visits. That was the constant. Okay, that's where I have to change something. Let's keep up with this for now. That's also where I have to change something. Okay, let's change things a bit in here. So we have to keep that up. Same that can be reached several times. We have to keep the frame in. If frame.child is less than frame.node.childNodes.length. Less than or equal to so we're going to use the child as a state indicator. If we're still within the range of the child nodes, we're going to do the standard logic, which also means the default value of 0 for the child, for the frame, is going to be treated as, yeah, we're still less or equal to the length, which could be 0, like in this case. In that case, we do all of that. That's increased by that. And frame dot child plus frame dot child. So next time we visit this node, we actually don't need to do anything anymore here. Frame dot visits. This can be reset directly. Alright, we go through that. If we're still in the initial phase, if this is the first time we run through it, we actually have to store the previous visits and update the current visit count. Then run the standard logic, which in this case or in this case will result in nothing else happening, just changes in the node, and in the end we change the visits and we can drop the frame. Frames dot top. The reason we don't pop up here is because we keep it alive. To get used by this. No, this is dumb. If that is what is 0, if this is the standard, we do all of that. And for this case specifically, God, I don't like this. I don't like state machines. I'm thinking, wait, I have to store the sum. That's an internal variable as well. Dang it. Means I have to store sum as well. And that's a score, which is another struct, which is gonna... Yeah, that's gonna take up some more space. Can't really do much about it. That was just the standard sum then. Yeah, that's fine. Gonna leave that in. If it's exactly 0. Okay, we're gonna do something in here. That means we're gonna set frame dot child equals 1. So child equals 0 means default setting. Child equals 1 means we're gonna do some recursive calls. I'm gonna have to check that in here. If frame dot child is greater than 0, then we have to do something. And if that something could be if frame dot child is less than or equal frame dot node dot ChildNotes dot length. Then we're gonna push the child node on frames dot push frame dot child frame dot node dot child nodes frame dot child -1. Have to start with that. Frame dot new frame child frame okay, like that, and we're gonna push the child frame. Gonna push it with the same node, so that can still increase, but that can have a different child count. We're not gonna hit the same frame, we're gonna hit a different frame with the same node potentially. The values still fit. We're gonna do frame dot child plus plus. Ooh, okay. So we know for next time child is increased. Nope, nope, doesn't work, doesn't work. Doesn't work like this because I have to return the score. So I have to keep track of that outside of the whole thing. When I pop, I have to store the value back. That means I have to store. Means I have a score return value. That, and I have to add that up when I return, when I pop. And I have to sum frame dot node dot sum, no, frame dot sum. That's only after everything is done. To take Child value equals new score. We're going to start with a new score every time we start with operating on children. That sounds weird. Let's not say that again. Oh, that doesn't make sense either. Okay, it's technically easy. In practice, difficult. You know what, instead of doing this the fancy way, I should probably just break this down into what's actually happening in the memory and recreate that on a straightforward stack. I mean, I'm basically there already. I have a state machine, kind of. Just that I have to share values in between. Okay, let's see what's happening actually. I start in the sum. So frame child is greater than 0. As long as it's in there, I am effectively within the loop. So I don't technically need the sum in there. I can just use that as the sum. Okay, I can drop the sum at least. That's good. Frames.pop. And what I add, frame.visit. Okay, that's, I'm adding it to the child. Once I've done all the children, I'm ready to pop down there. Actually, this is just continue then. Yeah, if I'm calling the child, if I'm adding it to the frame, I should just continue. So I process that child next and not do my stuff down here. Do that, and from subpop, if frames count greater than 0, if there are still frames left, then we're gonna take that frame before us, which is gonna be our parent, and we're gonna frames.peak. No, stop. Peak var 1 parent frame parent frame.node parent frame.visits -1 equal plus equals frame.node.scores frame.node visits. Okay, so if I'm done with my calculation, then we can join those two then. Wait, no. Can I? Wait. There we go. That also means we don't need the return value anymore. Can't forget about that. Since we directly added the value in the caller. We do have to make a separate if in here because we might change the value because of that logic. Alright, so first we always start up here to get that specific frame, which we keep in there for now. Since we might go back to it. We start always in here by storing the previous visits, so we can restore them in the end when we pop. We increase the number of visits in the node. When the frame, trying to make this 0, we do that logic and basically drop back down here, or we go through that logic up here and drop back, or we actually decide we have child nodes and we're gonna visit them in order. So we set it to 1. The state is now 1, which means the state of we're going state greater than 0. It's a state where we visit children, so next time we hit this frame, we're not here anymore. And first time we see this, we see child is 1, it's greater than 0. We iterate through the children, and as long as we're still iterating through the children, we're gonna push a child node with our child node, the index we get from our state, -1. And we just iterate or increment our child counter, so next time we go in here, we know next child, next child, next child. Until at some point we hit a point where we've hit all the child nodes, at which point we can also stop our own operation and just pop and leave the stack entirely, which includes resetting our visits, which is good. But also important, since we are going back, we are a child node of someone. The previous frame on this stack is our parent. So unless we're the very, very first node, frame counts is gonna be greater than 0. And we're gonna have frame before us, and we increase their score by adding our score. That should work. Public. Let's make a private static void CalculateScore. CalculateScore initial node. Let's see what happens. Setting breakpoint in here. We did have the big board, yeah. Actually, let's go for the smaller board first and see what's happening with that, if it's actually doing something or breaking. Okay, that was pretty quick. Relatively small board, 2000 nodes. Let's see if it breaks at any point. Yes, it does. This is an issue. What have I missed? So what's different about this? So we base it on our visits scores. That is pretty much correct. The visits that node has. I mean, yeah, that should be correct. And what we're doing here is nothing more than just that, right? Move on, let's quick check. Yeah, that worked, didn't break. And let's put that back out. See scores. Oh wait, you can't see what I'm doing here, right? Just checking currently parent frame has a node with 1 score. And node visits is 1, so up here we're hitting index 0, that's correct. But our frame has 2 scores, and we're hitting visit number 2. Which is of course out of range, so that's correct. What is going on here? Okay, let's see, we're doing this. Wait, when we call this on the node, it will increase the visit, but once the call returned, the visits are reset. So yeah, this needs to be like up there. And then we can just technically that should be the okay, we hit another problem here, but I'm kind of impressed that it didn't break earlier, so I'm quite happy so far. The issue was scores was 0. Did I? Is it if? Yeah, something isn't right here. Let's quickly go in there. So we are in our very first node, very first frame. Frames is currently only 1. That's correct. And our very first frame has now previous visits 0, which is correct. And the node has visits 1, which is correct. And we're hitting child nodes. Scores is resized. There's no one entry with zeros. So we're hitting up the very first child. Process the child, and so on. Which works up to that point, but then here's a problem because child node so 0 visits has 0 scores. Why is that? How did we get an array with 0 scores? It must mean we have created at some point a frame in here where the node doesn't get a new score, but if it's this, you create a new score with 1 entry, you will create a new score. This is where we update this. Okay, we create a new score array, that's fine. Here we make a resize to have at least 1 value, even if it's the default, and fill it. And if it's this, we still have the resize, we still have at least 1. Every frame starts with at least 0, in which case, no matter what is happening, we create a new array in here, or with this. Every node is guaranteed to hit one of those two, right? Let's quickly change something. Let's do string. There's this. If what's going on? If not is valid, return invalid. That bothered me earlier. Right. So let's get back to here. Create new frame with a node. New frames are created always with a node. Node dot scores dot length less than 1. If let's make a breakpoint here. Yeah, no, we are not. Things get weirder and weirder. So we have a node where the scores array is less than 1. But we're never hitting it in this loop. How? Let's do something crazy. So private static and counter 0 and public node public and ID. Let's do it like that. ID equals counter plus plus. Oh, let's do plus plus. So we start at 1. Alright. And then first let's figure out, let it break. And let's quickly see which node are we talking about. Child node. ID 3, and yeah, it doesn't have any score. Okay, ID 3. So the third node we generate. Did I add the wrong nodes maybe in here? Child frame? No, child nodes frame child. One child nodes. Is the correct node? No, that's fine. Okay, let's say if frame dot node dot ID equals 3. Let's see if we can hit it there. Nope, we never. How is it that we don't hit that node? That's shouldn't be possible. I am very confused by this. Right, we go through the motions in here. Sure. But we don't end outside the entire range. So yeah, we start with a frame child 0. It's always 0. That's always the same. Then when we decide we have children, we need to process first. We're gonna continue. And once we don't have any more children to process, and we get through the loop and hit our frame again, we're gonna remove ourselves from the stack, reset our node, and if we ourselves are a child, which is very likely, we're gonna take the newest frame on the stack, which is gonna be our parent, and update their score, which is correct. Child gets pushed, and the next iteration will go through that child, which itself might have children, which it pushes onto the stack. Always stacking the first child until we hit an endpoint. Either this or this. So basically this more accurately, or this. And then we jump back and go to the next child. So this is a truly depth first algorithm. Why do we not hit node ID 3? It exists. Therefore, it has to be the child of something. It can't just exist in a vacuum. Let's have a quick look. Child node. Where are we? Nodes. Generate map. These are all empty. I should probably iterate through this a bit more thoroughly. It seems like I'm skipping a lot of nodes. Right, let's quickly check something here. Map.values.count and scores.length. That's the one. Nodes is what I want. Nodes. Alright, so of our 2095 nodes, 2086 don't have any scores. So yeah, definitely have a mistake. Where am I going wrong here? Child frame is the new frame I'm adding, which is a standalone frame. Essentially, we're calling the method on this node, which is the correct node. Everything will completely iterate on its own from that frame in the next iteration of our main loop. But for now, we just have to remember that we have dealt with that child, we increase our own counter and continue to the next iteration. Do I increase child by accident somewhere? Oh. It's only used in here. That's not true, so that's not happening. That's true. And that should be perfectly fine. Let's go back in there. I'm not ready to give up yet. I'm so close. I'm so close to this. Right, let's just iterate through by hand and see if there's maybe an obvious issue. Size, child 1, and we add a child. Continue, right? And then we peek. That's a new frame. Do it right through that. We have to go through the child nodes and push that. And another child. Continue. Another child. Another child. We're at a depth of 7 now. Another child. This should be the last child, I assume. Nope, it's not. Another child. Weren't there like... There we go. With the maximum visits, so a node was repeated. So we pop this frame. reset the node to its previous visits. Then we take our parent frame. Alright, so that was an end state. This is a new frame. This is also an end state. Back. Another end state. I don't get it. Frame has one child node only. I don't see it. I don't see why it's not working. It should pass through all the children. What am I missing? It must be something obvious. It is not working. I mean, we know it's not working. I have made a mistake. Just where? Is it this logic? Okay, frames.pop. It's basically we return from our method. And when I do, I have to, before returning, reset the visits to what I've stored as previous visits. Which I've done so up here, when I entered the method initially. All of this is code I do when I basically enter the method, state 0, child 0. I take the frame and I store the amount of visits I have for that node, and I also increase the number of frames for that node. Let's just split it up so it's clearer, but that's what's happening. Could that have an issue? No, that shouldn't be. That references, that's fine. Frame is a struct. By design, it stores those all eternally, and node as a reference. That's also correct, because it's always the same node. No matter how many times we visit that node in different frames, or no matter how many frames we visit, it's always the same node in the background. It's the same. Then we do the logic here. We update the score. Which is fine, and then we completely return. Do that. Yeah, so this is something we do in the very first time we visit a frame. And only when we hit this part we actually bother with this sub branch, which is going to be hit the very first, after we hit this the very first time if we have any children. And we're going to hit it on every subsequent visit to the same frame. So we iterate through all the children, so that's correct. So we first process all the children. And every time a child returns, it will update our score, so that's correct. We've already increased the score array to make space for those visits, so it's, I don't see it. Like, maybe that condition too harsh. Child is 0, but child notes. Yeah, this doesn't make sense. Let's see. We had frame. Frame child is 0, so this is a first visit. But the node has children. We have child nodes, but that shouldn't be possible. Something went wrong in here. That's good to know, I guess. What happened? Visits is 2. Wait, what's our maximum visits right now? It's 2. Okay, that's why we hit our maximum visits. And therefore did this. So our frame node scores, so our frame has number of visits. We're gonna reset it to 1 later. We had 2 visits. That means scores 1. Wait, no. Wait, that part. So this should be the code we executed, right? Oh, right. Yeah, scores. No, that's correct. That's correct. I was looking at the child nodes array. Yeah, sure. 2 entries in here. That makes sense. The zeroth entry is still invalid or empty, so that's fine. And visits is 2, that's correct. That's a draw in here, so yeah, that's okay. Let's take another look at the next frame. So child 0. That means we hit another dead end. Visits 2. That's correct. Why are we only hitting the maximum visits? It's like we're always hitting the same node again and again. If frame.child greater than 1, let's make a breakpoint in here, see if that ever happens. Nope. So it's never iterating through another Okay, looking at the time, it's 3.5 hours. I'm not sure if I'm of the mind to complete this, but at the same time, I don't want to do another stream with the checkers. I do want to finish it. Okay, let's stick with it for a bit longer. Just a bit longer. We have the frame. Why would this never increase past? Let's quickly check something in here. Right, so frame.child is 1, correct? It's not 2, so next time it's 2. Child nodes. There are plenty of child nodes. And is that an issue? Because we... No, we never visit this again. Let's see, node ID is 1. Let's make a breakpoint in here. So we had node ID 1. Let's see what happens when we come back to this frame. 2. Dropping back down the stack. Two. Okay, we're back at node 1 where we were earlier. Frame child is 0? Why is frame child 0 again? I'm setting it to 1 in here, and I'm incrementing it here. I'm never resetting it. Let's start anew. Sorry. Frame node. Okay, this is ID 1. Which is our first node. Alright. Which has 4 child nodes. Child is now 2. If we look at the frames, it is 0. Oh, I'm in. Oh no, Oh, again! Because I'm a bloody idiot. Yeah. And it was so obvious. It was so bloody obvious. It's the exact same issue I had earlier. Exactly the same. It's a struct. It's a struct called by value. I'm copying the data. Yes, I'm updating this frame, but this frame is not the actual frame inside the array. It's a copy of the data in the array that's backing the stack. So of course I'm not actually changing the value in there. I'm not updating the previous visits. I'm not updating child. It's just... Right. I mean, I can make this class. Let's do that. Okay. Just to test its functionality, let's do it like this. Frame. Node like that. New. Let's just copy that line. Keep the other one in. New like that. And new frame. Shall note. Why did no one tell me that I made this obvious mistake? Could have said something. Anyone could have. Yeah, it's now actually working, so that's good. But I do want to use structs. So I'm wondering, can I use a ref struct in this case? I don't really have much experience with ref structs, so I'm not sure I can use that. Can't use that for a stack. I mean, there's always the option to make my own stack, so to speak. It wasn't... We used span earlier. Can't use it in this context. Where? Which structure allowed me to do ref structs? Memory? Read only span was ref span. It is a ref struct. Why can't I use it in... Can I... Yeah, I don't have much experience with span. Can I get a reference? without using the dark magic that we saw earlier. It's a ref struct. Can use it in a... that's not the point anyway. Guess we'll have to stick with the class. As much as I dislike using the class now. Not much I can change about that. I can change something else though. No, I can't, because I need the reference. That doesn't work. Yeah, so this is the limit of what I can do right now. I know there's a way to do this. Is there a way I can do this that's not making my own stack? Okay, let's first test if this actually does something good. Kind of sanity check or just see some result. So this took some calculation earlier. And we had a stack overflow once it was done. So let's just wait for the full 6.6 gigabyte to roll in. We're at 1.8, 19 seconds, 20 seconds at 2 gigabytes. Third of the way done. 3 gigs. Half a minute is over. We're on schedule. 4 gigabyte. Another 15 seconds. Oh wait, 20 seconds now. Was it? No, 1 minute and 8. That was what we had earlier. Right, so 10 seconds now. We're at 5.9 gigabyte. And there we go. Well, let's see what CalculateScore does now. Well, it's not breaking, that's good. Memory is increasing, we're at 7.4 gigabyte now. It did not break. It did manage to calculate. This is our board, and let's try to iterate through it. We're now using 7.7 gigabyte. It took 1.5 minutes to calculate, but player 1 won. How? I'm confused by this. So there was a mistake in there. Let's try the smaller board again. Let's make 4 and 2 pieces. Works pretty fast. It's a draw. Which, well, expected, kind of. Let's use 3 pieces. Let's drop the Alright, so we are at 3 pieces. Let's see what we can do here. Oh, the board is... Okay, this is definitely a wrong result, because I can see possible moves on both ends. So we did find optimizations, so I'm happy with that. And we can drop that. Don't care about that anymore. But there is still stuff not right. There's still bugs in here. And I'm not sure where they are, and I have lost all motivation to search for them. I did manage to get that end result. I'm tempted to go for the 8x8 full board. But considering how it increased with the previous data, I'm pretty sure I'm gonna run into some bigger issues than just my memory. For example, internally, the data structures I use integers. And we're running into counts that exceed the 2 billion mark. So I would have to create my own custom data structures that use something larger than integers. Maybe even a long wouldn't be enough, but at that point, if the long isn't enough, then my memory wouldn't be able to catch up to it anyway. So I would have to also find a way to store the data in less space. I'm not sure I can do much more with state itself. It's pretty compact already. Let's rename this again to custom BitArray. I mean, potentially some bits, and some bits could be saved. That's worth it, maybe. And of course, the different way of storing it all together. I mean, we've accepted the fixed amount of memory in the very beginning stage, designing stage. We accepted a bit more memory for the speed increase, which wasn't necessary in a way, but it's taking long right now and it's taking a lot of memory, so yeah, I think my approach is just ultimately flawed. It was doomed from the beginning. But honestly, I'm kind of happy with the end result right now. It is buggy. There is an issue, I'm not sure where, but it does set out the job. It generates the full tree. It generates scores for every possible move. And I can render the different states. I can render the game being played out. Let's do a 5x5 board with 3 pieces. Last attempt, and with that I'm gonna end the stream. See where this goes. The current evaluation function is just looking for the branch with the most wins. So that worked. Blue's capturing again, yep. Player 1 wins, and the last one shouldn't have been done. But that's the checkers solver. Checkers program, somewhat customizable, and kind of overboard. Not overboard, what's the term? Overkill AI solution. An attempt at a min-max tree that technically exists and works, sort of, even though there's a bug somewhere. And we actually managed to do some optimization today. Like, we are now able to actually calculate the end result of boards that completely broke the entire program before. And we learned something important. Reference, value type, very different. Always keep track of what actually you're using, because that's hugely important. It's so easy to forget. Yeah, I could definitely... I mean, this could be very easily replaced with an array. Or what means not very easily. I would have to rephrase every frame here to just an index. And we'd... Do I actually do that now? You're not... We're doing that now. Can't let it slide like this. I can't let it end like this. Frames equals new frame. Let's say we start with 10. Actually, no, let's start with 1. And let's make a little helper method. Private, actually not private, void push is gonna push is getting a frame, yeah, whatever. Frame, this is gonna take, we have the frames and we have the end frame index 0. If frame X. Wait, am I in the wrong place? Yeah, I'm in the wrong place. There. If frame index greater or equal to frames.length. Let's just do an array.resize. Frames and in new size length +1. Let's be very conservative, just increase by exactly 1. I have no idea how much it... How do I... It is only that little bit. Yeah, okay, let's increase it by a bit more. And length times... Times... By how much do we increase the size? That's 1.2. 20%. And yeah, has to end after that. And then we're gonna start out with a size of 10 to begin with. To make sure that we can always increase from something. And frame index. Frames. Frame index. Why do I have the curly brackets? Or the square brackets equals frame. Yeah, and we can increase that. And then we also have void up, which is just minus frame index. And we recreate peak, which is no wait, not peak. Or can I get a reference? No, I'm not bothering with that. And honestly, I only need to do this in that case anyway, so why bother? pushes only that case. Don't really need to do anything with that. Zero equals that. Child frame is added on there. Frame index. Minus frame index. Peak is if frame index less than or equal to 0. Yeah, that's fine. Else frame index -1. And we can drop that. Or frame index frame index -1. And we're gonna have to change frame everywhere now. Can I actually... So, like that. Let's see what it's doing. Nope, I made a mistake. Ah, I'm changing the frame index, right. Because this referred to the old frame. That means I have to actually, instead of -1, I have to use the frame index as is. Wait, no, something is not right. That was my pop before. I did... Yeah, that is correct. I still had my frame index. That was correct. Let's reset this. And current frame is frame index -1. So what I want effectively is frame equals times current frame, right? So if I do this with class frame, it should work? Question mark? Since I still have the class and everything? Yep. All right. And now let's replace frame with that. And yeah, current, not current, correct, current frame, like that. That should also still work. Seems good. And now, finally, I should be able to use a struct. Yes. Woo! Okay, let's quickly make a comparison. What's the difference? If I use a class. Okay, that was after about 8 seconds. I'm at 692 megabyte. Actually, let's make a breakpoint in here. There. Six, 7. Yeah, 7 seconds. Okay. In the debugger, I have 8.397 seconds and 692 megabyte. 8 seconds to about 700 megabyte. With a lot of garbage collection. Let's see what it's doing when I change this to struct. About 7 seconds, 7.7, and still the same memory. So it's slightly faster. Let's have a comparison of just the CalculateScore. Let's drop this. All right, so this is with struct. Okay, and go. 845 milliseconds. And garbage collection is happy. Let's try again. This time with class. All right, and 1.251 seconds. And garbage collection is also happy. Alright, let's see how far do we actually go with the resizes here. What happens if we do resize times 2? So struct is faster. Just 8.49, so that didn't change too much. What happens if I just use length +1? I'm pretty sure garbage collection is not happy with me anymore. But then again, I don't know how big your thing will get in the end. Oh yeah, that's taking a lot longer and memory increases a lot more. Actually, let's make a quick check down here. I want to know how big does the array actually get in the end. Okay, we're at 1.4 gigabytes and frames 14105. 14185. Okay, let's try to get there. 14185. Let's see what happens if we initialize the array with exactly that. Oh, wait. CalculateScore like that. Also, let's put in the old rule. 1.2. Worked quite well. And let's see what happens. $831, so it's not really doing much. Maybe a minimal increase in memory efficiency, since we didn't have to allocate the same array multiple times. but overall was fine as it is before. So yeah, the struct method actually did work. Could have done that from the beginning. Got rid of the recursion. Which also meant getting rid of the stack overflow, because this stack, or this frame stack, this array is hosted on the heap now, not on the stack, so we can make use of the vastly greater amount of memory and space we have there. It's based on structs also, which makes it a lot more efficient for lookups. Yeah, I think I'm happy with it. I can put this to rest now and not feel like having a restless night over it. Alright then, let's do a 4x4. This time for real, the last game. Not full 888, 442, but our last game. Okay, that was kind of dumb on both sides. Then again, the way I coded the comparison method, player 2 is now actually playing to lose. So I guess that makes sense. Player 1 is playing to win, and player 2 is playing to lose. They're both trying their hardest to do exactly that, with more or less success. For example, this was not a good move to lose. So yeah, I'm definitely evaluating this stuff wrong. But that's our checkup program. What do we do next time? I am not sure. I'm definitely going to start the Introduction to Programming series again. I'm gonna make this a yearly thing and just basically always start that series again for new people that are coming in. But maybe I should do some other stuff in between. So I'm not sure. Maybe next time I will start the series again, or we'll do another project with programming. I'll have to think about it. Right, then lovely Sunday to everyone that still has a Sunday. And possibly till next time.